Um, Hello, everyone. My name is Jing Wang. Thanks very much for joining this presentation. This presentation, I'm going to talk about the design protection scheme for 100% renewable microgrids. This project is funded by Area Internal Funding, LDRD. So we have a team to work on this topic. In a high level, we think this is a very interesting but a very challenging topic. Microgrids with 100% renewable, there's many challenges there, controls, protections, and others. So this is particularly focused on protection. And we will see what we have find out. And in this presentation, we will start from the generic concept. So that's the part one. We will talk about the protection challenges for the 100% renewable. And then we will also look at the IBR inverter-based resources for the characteristic. With that, then we will use the example microgrid as a use case to see how you can do the full study and use the traditional protection design to design the protection for this type of microgrid. Then we will also talk about the data-driven protection. Finally, we will wrap up and show you some key takeaways from our work. With that, we would like to get started. For the 100% renewable microgrids, as you know, for example, here, there's no example shows there's no single generator type of conventional units. All are renewable or inverter-based resources. There are many challenges there. We highlight a few of them. For example, the variations in fault current. As you know, the microgrid has grid connected and isolated mode. The fault current level is very different in these two modes. Based on the study, it shows grid connected and the fault level in the grid connected is usually at least 3 to 7 times of the isolated mode. So there's a big difference. And also the IBR operation modes. And a lot of IBR also 1547 compliance. Those affect the IBR fault current output as well. Plus the weather conditions. For example, if there's full solar or no solar, the PV inverter output for the current is also different. And the power flow is usually bidirectional in this type of microgrid. So this affects the directional element as well. Plus the phase angle of the voltage and the current, they sometimes is not consistent. There's some jump up and down with different changes and finally settle down with a certain value. These changes and inconsistent affect the directional element as well. Also, the symmetric tripping because of the short line impedance and makes the relay see the same fault. Relay sees the different relay sees the same fault response, so avoid cause the unnecessary tripping. Other factors like no inertia or limited short circuit capacity, all those lead to a dramatic change in frequency or voltages and the scarcity of the low-cost protection devices. So all those are the summary of the challenges in 100% renewable microgrids. In the next few slides, we would like to see in a little bit more details, see how the IBR for the response look like. First of all, inverters do not dynamically behave the same as synchronous machine, and they don't have the fault current based on the characteristic that a traditional machine has. Also, the fault current has much faster decaying envelope compared to the traditional machines. The IBR usually have control loops with different time constants. This also impacts the fault current characteristic of the inverter. Overall, we think inverter behavior is largely software or firmware defined. The filter determines the subtransient or transient response, and the type of controls implemented determines the steady state response. Based on the standard, the fault current contribution of IBR usually is from 1.2 to 1.5 times as the rated current. As we know, the controls affect the fault current, and then we have 3 types of controls: grid following, GFL, grid forming, GFM, and grid supporting. The GFL inverter are referred as current control because current is a physical quantity that is regulated. They lead the grid voltage for operation and the synchronization. They usually control to inject the real and the reactive power. For the grid forming inverter, they provide functionalities that are traditionally provided by synchronous machine, and they can be designed to control or establish system voltage and frequency. Grid supporting control either can has grid following control or grid forming control. Because of grid supporting control, either is grid following or grid forming control. So we only look at the grid following and the grid forming control. In high level, these two grid following and the grid forming IBRs, they have very different fault characteristics. So for example, this slide shows the grid following IBR without 1547 compliance. This is a typical control structure. We have a power control, current limiter, and then current control, and also the PIL. The fault current of IBR is a function of the control scheme and as well as the physical components of the power electronics. Analytically, we can calculate the fault current of the IBR grid following inverter. Like here, you can see it has a steady state and a transient state. For example, the pre-state is determined by the pre-fault power current reference, and this here shows the transient, and also the steady state if it hits the limit. As you can see, for the transient, the low pass filter cutoff frequency affects the transient dynamics. Here we have one example. When the voltage goes low, for example, step response from 1 to 1/3 pu, and we can see how the current look like. It experiences transient and hits the limit and then saturated. So that's how the inverter output fault current look like under the scenario without a 1547. And the next slide will show you with 1547 compliance how the grid following inverter fault current look like, because this is quite important feature to look at. So as you can see here from the table, this is the trip and the low voltage residue of the grid following inverter. For example, we have the category 3, and we only look at the condition with a low voltage area. For the momentary cessation, we can see the inverter will keep the power injection for the first 5 cycles and then 0 thereafter. The inverter stop gating but remains connected. And for the sys to energize, it will stop the power injection and the trip. And you can see the 1547 logic is actually added to interfere with the power reference generation. That's how it responds to all these requirements to do either keep injection or either momentary cessation or sys to energize. The next slide shows you analytically how the in the different voltage area how the current look like. So for this equation shows the current reference calculation. P star and Q star are the power reference, and then V GABC is the terminal voltage magnitude, and then this is the phase angle of the voltage for synchronization. So this is how the reference generated based on different range of the voltage or severity of the voltage of the fault. So you can see the output current. I is a grid following inverter output current, and the max is the maximum current. Usually is 1.2 pu. So you can see with the voltage lies in different range, and we can see how the output current look like. Based on this, we can understand the current limiter of the inverter dominates the output current response. And once the maximum current is hit, the grid following inverter behaves as a constant current source. For the low voltages, the inverter will inject current for the first 5 cycles and then stop the injection. This is a momentary cessation. And the initial spikes of inverter depends on the inverter filter, the fault voltage, and the point on wave timing of the fault. And people also care about the DC source. Usually the DC source typically do not heavily influence the fault response. So this is a summary of the grid following inverter with 1547 compliance. For the next few slides, we will look at the grid forming inverter. So this is a typical control structure of the grid forming inverter with outer loop, the grid voltage control, and then inner reference for the inner control current loop, and then current limiter and the inner current control loop. And for the photo response of this grid forming inverter, they depends on the inverter hardware configuration, the inverter control strategy, the current limiter method, and the reference frame in which the controller and the current limiter are implemented. Usually, the photocurrent will be larger than the supplied photocurrent by the grid following controls, especially for the negative sequence current. And this type of control usually have faster response of the photocurrent compared to the grid following control, because current is not directly controlled, so it responds much faster than the grid following inverter because they are regulated by the current controller. To look deeper of the grid forming inverter response, and we see under the symmetric and asymmetric fault. For example, under the symmetric fault, we see the grid forming inverter output voltage and the current are balanced. In this case, inverter voltage control cannot track the reference due to the reduced terminal voltages. I know people use the virtual impedance control to compensate the delay, reduce the voltage, and to make the tracking better. But under very severe fault, the voltage reduced significantly. There will still be deviation there. So that says this type of control might or might not saturate the inner current loop, even depending on the severity of the fault. In general, the terminal voltage will experience a step change with transient as shown here. So the V0F is steady state, and then here this is the transient. Tau is the time constant. It's related with the low pass filter in the power sharing. And actually it's the low pass filter cutoff frequency of the power measurement. And we'll also see the output current experience the step change as well. It has similar response as the voltage, as you can see here. Usually the maximal current is limited to 1.5 pu compared to the following device. So this is under symmetric fault, and this is only the positive sequence. For unsymmetric fault, so we see they usually include the positive, negative, and zero sequence components. For example, if the PI controller is used, it cannot be able to regulate the VDQ into their target value, therefore resulting tracking error. This tracking error might or might not saturate the current controller, the inner current control loop. And if it saturates, then the system will be unstable. It will have very messy output voltage and current. Overall, if the current limiter is not heated, so we can consider the grid forming inverter as the voltage source connect with the impedance, and it has a positive, negative, and zero sequence. And then we can use this equation to represent the dynamics of the grid forming inverter. If the current limiter is heated, then it will be shown as the current source and parallel with the impedance, and as you can see here. And you can use this equation to represent the dynamics in the three, the positive, negative, and zero sequence component. So for the negative sequence, it appears as a double harmonics in the DQ control. So it can be used to detect if we use the negative sequence component, we can use that to detect the unbalanced fault. So this is not a very deep evaluation of the fault response of grid forming inverter. This is a still very open area, and a lot of research is doing. And so this, what I'm showing here is just to give a direction if we want to investigate the fault response of grid forming and grid following inverter, which direction to go. Yeah, so this is a generic talk. In the next many slides, I'm going to use one example microgrid and see how we can design the protection scheme with a 100% renewable microgrid. For the microgrid, we use the Banshee benchmark microgrid. As you can see here, we take the feeder 2. We have the two circuit, 201 and 202. And we have multiple grid forming battery inverter and multiple grid forming PV inverter. And this is a three-phase system stand for the commercial or industrial microgrid campus. For the grid forming inverter, we use grid forming control in both grid connected and isolated mode. For the grid following inverter, it has 3 operation modes. We will show the inverter control in the next slides. And we use a constant impedance load. In total is 4.7 megawatt. Those include balanced and unbalanced loads to make the fault detection more real. We use constant impedance loads because it will not contribute any fault current. If we use a constant power load, they are modeled as controlled current source. They actually contribute fault current, and that will make the fault current contribution unrealistic. That's why to have a correct load modeling is quite important. For the relay and the circuit breaker, we actually simulate 5 cycles of mechanical delay to emulate the physical delay in the circuit breaker. And we have the PCC relay here. It can control the microgrid for grid connected and isolated mode. So this is a high-level description of the benchmark microgrid we used for the fault study and the protection design. For the grid forming inverter control, as you can see here, it has a power level control and the device level control. For the power level control, we have the power tracking in grid connected, so the integrator is enabled, and so that it can track the power reference. For the isolated mode, we have the VF power sharing control with the integrator disabled, so it can do the power sharing. And this grid forming inverter is 1547 compliant in grid connected mode, because many grid connected inverter has to be this 1547 compliant. That's why we added that logics as well. As you can see here, it interacts with the controls to be the tripping and the setting, tripping and low voltage rise to compliant with all the defined threshold and the settings. For the inverter control, it has a virtual impedance control, voltage control, and current control. This is quite a standard in many grid forming control. And for the inverter modeling, we use the average switching model. So we have the constant DC, and then we have the switching PWM modulation emulated to emulate the switching dynamics to have a relatively more detailed modeling. So this is grid forming inverter control and modeling. For the grid following inverter control, as you can see here, we have the fixed power factor control, PQ dispatch, and the volt-var control with VAR priority. These are very typical control functions in smart inverters nowadays. And we don't use the Joule control for the power control. PIL is used for the synchronization. And this grid following inverter is 1547 compliant as well. As you can see here, we added the logic to interact with the power reference generation. We also use the average switching model to emulate the switching dynamics. So this is the grid following inverter control. In the next slide, I want to talk a little bit about this. What are the challenges what we see with this specific 100% renewable microgrid? First of all, in the isolated operation, the source of the fault current contribution are the battery and the PV inverters, because the battery is 1.5 PU maximum voltage, and the PV is 1.2. So the fault current is really low, and so therefore, the definite time or instantaneous overcurrent protection is used instead of inverse time in the protection in the isolated mode. The PV has very varying output current due to the changing solar irradiance, and the relays across the microgrid can see different normal operating and fault current. This implies the threshold-based overcurrent protection may not be sufficient for the protection design. And due to the limited fault current and the short lines across the microgrid, the voltage profile seen by given relays might be the same. Therefore, using voltage-based protection cannot be efficient to differentiate fault just using the voltage-based protection. And for the negative sequence current, it is actually very changeable. And we have to add a positive sequence component to detect the unbalanced fault as well. So those are the findings we see, or the challenges we see for the protein design with this microgrid. And the next slide shows our workflow based on our study and the findings, how we design the protection. First of all, we do extensive fault study running thousands of scenarios, simulation scenarios, and we extract interesting fault signatures and analyze them. Based on that analysis, we design the protection. For example, we first define the relay category, and then we define the communication architecture. We also use the direction elements and the sequence components for the protection design. Also, rate of change is used as well. Time correlation is used to correlate between different relays for the primary and the secondary relay correlation. So, and with this, we implement all those design rules in the MATLAB, and then finally we perform the simulation and test them, see how the design the protein scheme work under a lot of different fault scenarios. So this is the overall design flow. So here we show the fault study because that's a very important part for the protein design. We run the automatic script in MATLAB Simulink, run hundreds or thousands of scenarios, because we actually have annual solar and load profiles, but we cannot run so many scenarios. So we did actually pick up the 8 days, which are represented to be like a yearly profile, represent profiles for a year, and then we follow the predefined test metrics, as you can see here. For example, we change the inverter control mode, the conditions, solar irradiance, power factor, and the loading as well. And then we have different fault locations and a different load fault type and the fault impedance. We also change the microgrid operation mode, reconnected or isolated mode. So this is a test matrix. With that, for each test, we extract some fault signatures. For example, the instantaneous voltage and the current, and the voltage and the current RMS, voltage and the current sequence components, and the rate of change of positive and negative sequence of the voltage and the current as well, and the rate of change of frequency and as well. So all those features we extract, and with those we then analyze which are the interesting indicator to say there's a fault there. So that's how we extract the essential features to do the protein design. So for the protein design, overall, we use the adaptive and the communication-based design. Adaptive is necessary because of different operation mode of microgrid and the different PV and the loading scenarios. For the relay logic, we have the fault detection block and the tripping block. So the fault detection block detects the occurrence of a fault based on the measurements and the design logics. And the tripping block, once the fault is detected by a relay, the fault signal goes to the tripping block where the trip signal is generated. And this trip signal is generated only if the relay does not receive any block signal from adjacent relay. So this is a high-level description of the relay logic. Overall, we have 14 fault locations, as you can see here, from F1 to F4, and we change the fault location, fault impedance, and the fault type. And for certain, for each fault, there certain relays need to operate. So this is the protein design. And then let's see what we have used to design the protection. First, we define the relay category. As you can see here, we have the relay that's only load collected. We have a relay on top of the feeder, like 201 and 202. We have relay collect with battery, we have relay collect with PV or relay collect with PV and the load. So how we define the relay category? So we base on if the power flow under fault, it is deterministic or not, then we define the relay category. For example, category 1 is a relay that collect with load or PV or with load and PV, because under fault scenario, the power flow is deterministic. So this is relatively simple category. Those relays are long adaptive and long directional. It's easy to detect the fault, and they use sequence components for fault detection. The relays including 204, 206, and many others. And the PCC relay is also category 1. We have also category 2. Those are on top of the circuit and also with the battery connected, because the power flow is more complicated. And those relays are more adaptive and directional. They also use sequence components as well. Those relays include 201, 202, and the others relay, as you can see here. So this is an important step to define the relay category. Then we define the communication. As you can see here, we have 6 groups, and each group have multiple relays included. So the relay, the group, the relays inside the group can share information, and also relays with can share information with adjacent group. For example, group 2, the relays can share information with group 1. And for the communication, we have 2 types of signals defined. We have a transfer trip and a blocking signal defined. For example, if there's a fault happened as here, F6, then the 202, we call it a responsible relay. Then it will send the transfer trip signal to the downstream relays, including 209, 210, and 211. So this is a transfer trip signal. And it also sends the blocking signal to the 201 and the PCC to avoid sensitive or unnecessary tripping. So these are 2 types of signals defined using the communication. And we also have PCC circuit breaker status being shared within relay. The relay in group 1 will further transfer the PCC circuit breaker status to adjacent relay, and so on and so forth. So all the relays in the system will receive the PCC circuit breaker status with different time delay. And then with this status, so they will adjust the protection settings accordingly if the operation mode is changed. So this is another important aspect for the protection design. And we also use the direction elements, is to differentiate power flow in the forward or reverse direction. This is pretty old school, so I will not talk too much, but in a high level, the grid connected mode relays only need to detect the fault in the forward direction. And in the isolated mode, relay with battery connected only need to detect fault in the forward direction. But for the relay 201 and the 202, they are located on the top of the circuit. The situation is complicated. They need to detect both directions. So they have DIR1 settings, that is for forward direction detection. And the DIR2 is for the reverse direction. You can see what are the settings there. And also you can see in the isolated mode, the direction that we use to differentiate the fault 5, 6, and 2. So those are responsible by the 201 and 202. They should operate accurately using this to differentiate which fault it is there. So this is directional element. And the next slide, we will talk about the sequence components. We have the differentiation between category 1 and category 2. For example, for category 1, we have different pickup level and settings here. For example, this 204 and 201, 208, we have the I1 is a positive sequence. If it's bigger than 2.5, then it will trip. So this is used to detect the balanced fault. And for the unbalanced fault, we have all. So if unbalanced fault happens, then if the relay sees the positive sequence is bigger than 1 PU, and then the negative sequence is bigger than 0.3 PU, so it will trip. If this condition matches, so it will trip. used to detect the unbalanced fault. So we can also see the different pickup level for other relays. So this is for the category 1 relay in grid connected or isolated mode. But for the category 2 relay, we have difference in grid connected and isolated mode, as you can see here. I will not go through each of them, but just a high level to say we need to have different settings there. So that's how we do adaptive in grid connected or isolated mode. And we want to mention is for the 201 or 202 relay, during the isolated mode, we also use the voltage positive sequence to detect the fault as well. It's necessary to have this one, otherwise the detection will not have good accuracy there. And all this threshold is based on extensive fault study, and we find the threshold that work for most of the situations and the scenarios. We have other factors, the time correlation, for the grid connected and isolated mode, time correlation is different. For the relays located by the end of the feeder, then they have relatively short time, and if they connect by the top of the feeder, they have a longer correlation time delay. And as isolated mode, the time delay is bigger because the power flow is more complicated. It needs more time to decide which situation it is or which direction it is. We also use the positive sequence current rate of change to detect the fault as well. So with this, we design the protection. We call it a traditional protection design. And then we enter to the simulation validation. For the simulation setup, we also use the automatic script to test many scenarios. And the simulation is running with 50 microseconds, and the relay sampling time is 6 kilohertz with a system base of 1 MVA. We run different fault location and attacks. We only run the low impedance fault because it has challenges to detect the high impedance fault. That's the future work. And we also simulate different solar and load profiles, but still limited scenarios. PV operates in fixed power factor, and the battery SOC is high, and all loads are balanced in situation. Fault is applied at 3 seconds and removed at 3.5 seconds. Overall, we run 56 cases in grid connected mode. We see the accuracy is 94.6% accuracy. And the isolated mode, we run 52 cases with 86.5% accuracy. So you can see the accuracy rate is actually quite good, and we see the grid connected is more challenging. As again I mentioned, this is under limited scenarios. So you can foresee for the traditional protection, this is a big challenge there. For your interest, we put a few simulation results as shown here. Let me move this. We start with grid connected mode, and to test the category 1 with the fault 8. So we can see we actually run with different solar irradiance. We realize because it's grid connected, the fault current from the grid is dominant. So there's no difference in full solar or low solar or very few solar scenario. And the different fault type have different big impact on fault level. For example, in this 3-phase fault, you have really high positive sequence current, but for the line ground fault, you can have much lower fault current level. And so you can see the fault type impact the fault current level. And with this test, actually the results here is with the full solar. So we see how the circuit breaker respond. And the 207 is a responsible relay. We see after 6.6 cycles, it will trip, and it also sends the transfer trip to the downstream relay. So 7.5 cycles, the downstream relay open the circuit breaker to isolate this fault. And 6.6 cycles includes 5 cycles of mechanical delay. So you can see the actual delay detection time is 1.6 cycles. It's really fast. So this is with this scenario. And we do the same simulation with isolated mode. we run the scenario with the full solar and low solar. You can see with the full solar and the low solar, the fault level is different. So that's why, and that they're different but relatively close as well. So that's why overcurrent protection is usually difficult to differentiate, or you have to do a lot of study to find a very good threshold to detect them. And for the interest, we just look at the full solar scenario, and we can see for the relay 207 is a responsible relay. It sends the transfer trip signal to the downstream relays, and this relay trip after 3.16 cycles with 5 cycles mechanical delay here, and then downstream relays is 9 cycles after fault they tripped, and they operate as expected. We also look at the battery and the PV. We can see both battery and the PV, they return to normal operation after fault is cleared. You can see during fault how the voltage and the current look like. And then once the fault is cleared, they return to normal operation. So you can see with very good protection, the microgrid can continue to operate as normal and without interruption of the power supply. We also see the category 2 relay with the grid connected mode. You can see under different fault scenarios and how the different sequence components look like. So the conclusion is similar as previous category 1 relay under grid connected mode, and the relay tripped as expected. So PCC relay is a responsible relay in this case, and it tripped 6.9 cycles after fault happened, and the downstream relay 7.8 cycles tripped the circuit breaker. So the relays operate as expected. We also see how this same scenario works under isolated mode. We simulate both low solar and full solar. You can see the phase angle because we use the directional element. And for the interest, we show the full solar scenario. And here we use negative voltage, negative current, and then positive voltage. You can see the pickup level, and they meet all the triggering threshold, and then that's why relay detected. But it is either 2, 5, 3 fault. But because we use the element direction, we identify is a reverse direction. So we know it is a fault 2. So that's relay trip the circuit breaker and then identify the fault and isolate the fault. So the relay 202 and 201 trip the circuit breaker. After 10.5 cycles, it takes longer time than the grid connected mode, and they didn't receive any blocking signal, so they trip as designed. So these are the representative results for the isolated mode, and also it shows the circuit breaker operate as expected. Now, I would like to recap the protection design for this work using the traditional protection. So we can see category 1 relay works pretty well under all different scenarios, but the category 2 relay need more testing and the modification are needed if conditions are changed. For example, different solar irradiance, different PP operation mode, etc. And the 15447 compliance affects the fault response, but the traditional protection still functions. In general, the workflow we designed in this work can be used for other microgrid as well. So you probably need to do some first study to update your threshold and the settings. So that's what we learned. For the performance evaluation, we can see with the limited scenarios, we can see it functions, but it's still challenging to detect the fault under a wide range of scenarios, under all sort of solar and load irradiance and unbalanced fault as well. Some faults are difficult to detect, such as line ground fault at 3, 11, 12. We see they are located at the delta side of the transformers. So the negative sequence component is messed up. So that's why the detection is challenging. So we will work on this in the future. Limitation we see is protein does not function well under various solar irradiance, and also high impedance doesn't function as well. And under unbalanced fault, it need to retune the negative sequence threshold. So overall, it is, we test the limited protection scenarios with a more wide range of scenarios. The testing is needed and the modification is needed as well. That's why we need a better protection that can learn the patterns and recognize all these features with thousands of scenarios and situations. Because traditional protection cannot do all of this. That's why we need data-driven protection to do this. So this is what we see using traditional protection. So that will help us transit to the data-driven protection. And that's why we use data-driven protection design the protection. We did some homework. We first see what has been done. For the existing work, the fault identification can be modeled as an anomaly detection problem, and the estimation of the location of the fault can be modeled as a regression problem. And the fault location in the network, for example, a microgrid, can be modeled as a classification problem where each location in the network is responsible for specific relays. This is what we did do in this work. And there are limitations with existing work. For example, the data set are not representative for all the scenarios. Imagine you have 365 days and you have so many different scenarios and how you can include all of them. So that's a challenge. Machine learning method need to have much more, they have only operate under specific conditions. So cannot guarantee to perform when operation conditions changes. And the varying fault parameters require the machine learning models to learn from diverse fault scenarios. Apart from that, they are also centralized. So the learning method often require all the measurements to be collected as a central unit to be processed by the machine learning approach. With distributed relays in the system, this is unrealistic. So this is a work we have, literature we have done and we are going to improve up on. So we will show you what we have done. To start with, we want to show you the workflow. As you can see here, we have 3 stages. Stage 1 is data generation, and the stage 2 is data extraction and feature extraction. Stage 3 is we use support vector learning machine classifier to localize the fault. And for the fault signature, and you can see here, those are the different things we change to have thousands of scenarios. And we actually have balanced and unbalanced fault to challenge the design. And for the recorded features, we have positive, negative, and zero sequence components, DQ0 components, and harmonics as well. And so each relay is designed to collect all these features. For the training, we train multiple classifiers where each classifier is to be deployed at a specific relay, and we assess the performance of the classifier individually and the performance of the whole approach. We also want to show you what scenario we simulate to get the data generation, because this is particularly important for the data-driven protection design. For example, for the fault parameters, we have also 14 fault locations. We use the discrete uniform over locations to randomly generate the fault location. And we have 4 type discrete random over types, balanced and unbalanced fault. And we have fault impedance from low to high impedance. We have beta distribution with 2 peaks to create the fault impedance. And we also have fault time, and we have uniform continuous way to generate the fault time. For the operating conditions, we have solar and the loading conditions getting from the annual real data. And then we have a inverter operation mode from the discrete uniform over modes. We have microgrid or grid connected or asymmetric mode. So this all combinations together, we can create thousands of simulation scenario. So this is what we have did for the data generation. And for this method, we actually see an issue. The data-driven protection scheme has a problem to differentiate the fault. For example, here we have a relay 219. It sees the exactly same fault features with fault 11 and fault 6. But the fault 11 and fault 6 requires different operation for the 219. With this, how can we design So we realize this problem, and we say this calls for correlation mechanism that a relay can delay or block tripping relays that cannot clear a specific fault. So make the relay operate correctly. So that's what we learned from the study. With that, so we design the correlated data-driven protection. So that can be used to help to distinguish fault signatures and share information and block tripping. And we simplify the task of classification at each relay to classify the direction of the fault, upstream or downstream. With this approach, we have two stages: the measurement sharing. So that's how we share the measurement, and then we know what happened with other relays within the same group. So each relay communicates within the labeling relays measured voltage and current. This enables the relay to accurately classify faults. We also have the decision rules. So relay decides on the location of the fault based on the classification at all labeling relays. So these are the two important the techniques that we design the protection using data-driven. The next slide shows you the measurement sharing. For example, we have all the relays. You can see the relay 201 sharing relay measurements from the relay 202, 205, 206, and 207. And then we can also see how other relays share the information. So this is the first step. The next step shows the detection zones, also communication-based detection. So we actually have defined the 6 zones, as you can see here. The zones is designed to correlate between zones and then see if the relay is within that zone or outside of that zone or responsible relay. For example, for the decision zone 1, if fault 2 is to detect the fault 2, and if there's left branch fault, then we think this responsible for the decision zone 2. If the fault happens in the right branch, so we think it is the responsibility for the decision zone 4, then it will not do anything. And then so on and so forth. It will have like a chain reaction to, if it's its own responsibility, then it will respond. Otherwise, it will check and then go to the next one, so on and so forth. So that's how they communicate and share the information to avoid wrong tripping. So this is, I will not go to details how each of the design, you can see from here. But for more information, we would like to see how we design the logic in each decision zone. So here we have 1, 2, 3. For example, in the decision zone 1, we have defined 0, 0. Then we can see it's a fault 2. So then this 2 relay will trip. If it's 0, 1, we think it's the responsibility for the zone 4. Otherwise, if it's 1, 0, it's zone 2 responsibility. If both are 1, 1, then it's inadmissible. So it's non-detectable. Or nothing happens. So this is zone 1. And we can see zone 2, it has 3 relays. So it has more combinations and much more complicated decision making. And you can see with different value, what are the decision making. It has more inadmissible results. And for the zone 3, we can see a similar thing as 1 as well. So this is the first 3 zones. And the next slide shows the another 3 zones as well, 4, 5, 6. The decision is made by similar way. We can see this zone 4 has 3 relays. So it also has similar feature as the zone 2 has more combinations and more complicated. So this is how we define the decision zone. There are a lot of design and implementation details. Because of the time, I will not go through all of them. So I will not just I will just jump to the results directly. So for the design, we use the automatic script to run 1,000 scenarios with 700 scenario for the training and 300 scenario for the testing. So here we use the small vector machine classifier with polynomial colors for all relays in the microgrid. And you can see the results here from all the relays. As you can see, we have the precision, recall, and accuracy. Basically, you can see here the relay that's by the end of the feeder, they have relatively simple detection and simple decision making. So the results has actually higher accuracy, but the relays on the top, they have relatively low accuracy compared to others. And in the future, we will optimize the classifier to obtain better performance. So with this work, we see this type of approach function, and the result is not that bad. So the future work it gives us confidence to follow this approach. The future work will be to improve the accuracy or performance of the classifier. So that's how we did the data-driven protection. And we also show the accuracy for each decision zone. For example, zone 1 and zone 4, they have relatively low accuracy because the decision making is more complicated because of the power flow direction and the situations. And the decision zone is decision zone that is located by the end of the feeder has a much higher accuracy. And one thing I want to mention is, as I said, is one pass to each zone will check and then pass to the next zone to the next zone. So there's the accuracy dependency there. So if we have very high accuracy of zone 1 with the 201 and 202, and then the overall accuracy will be improved because they are actually located in the hub position. Every checking need to go through them. So this is our future direction as well. Apart from improve the classification accuracy, the zone 1 classifier is the most critical one that we will work on. And then we come to the results and the performance evaluation. For the overall accuracy is 65%, as you know, we run 300 cases for the testing. One example is, for example, if there's a fault at 8, then relay 201 and 202 is 10. So it asks zone 2 to make any further detection, and then zone 2 has these 3 relays 001. Then it let the zone 3 to do the further detection, and then zone 3 finally find out is 00. So they detect is fault 8, then trip the signal, trip the circuit breaker. So this is how we define the identify the fault location and the trip circuit breaker. With all the tests we run, we have this time to locate the fault, and so you can see it's actually quite fast. It's less than 2 cycles with all sort of scenarios we run. We're connected as landed, high, low impedance, different fault locations, and different solar and load irradiation profiles, and the PV operation modes as well. So, so it is a very comprehensive test. And the classification delay actually depends on how many numbers of decision zone to be checked. If only one zone is checked, so the delay is much lower. If we have the fault is by the end of the feeder, so many zones need to be detected, so the time is relatively longer. And the advantage of this approach is the heavy burden is shifted to the offline training, so the decision-making time is very short. So that's important for detection because we need to really respond accurate and fast. And we observe that relay 201 and 202 are very important. So if we improve the accuracy in these 2 relays, the overall relay protection accuracy will improve significantly. And also for the feature fault signature dimensionality contributes to the more accurate classifications. If we use 10 features or use 20 features, 20 definitely much accurate and better, but the computation complexity is much significant as well. And we have very good accuracy for the high impedance fault, but the accuracy still need to be improved. So those are the.
Hey, Jing, this is Brian. I'm just doing a quick time check because we're a couple of minutes on the hour, and there might be a couple people some people that need to jump off at the end of the hour. How many slides do you have left? I'm just
I
wondering.
have two.
Okay.
Actually, two.
All right. Well, then
Yeah,
I'll just let you continue and see if we can get to a conclusion here soon. Thanks a lot.
Sure. Yeah, you're welcome. Sure. So now let me recap the data-driven protection design. So this data-driven protection approach has can handle situations, complicated situations, running thousands of scenarios to solve those challenges that the traditional protection cannot resolve. And the learning-based approach requires a careful design of communication between relays, and the use of representative fault data samples is quite important. And we also need to design simple learning tasks for each machine learning models so that it can respond faster and have faster detection. And the hierarchical localization approach to identify fault location, it is a very good approach to follow. And we have achieved a very good performance with different scenarios and the high impedance fault as well. So I think this is a good direction to go. Now, this is my last slide. I want to highlight the key takeaways we have for this project. Overall, the 100% renewable microgrid has a lot of protection challenge there. And we find out grid connected and Atlantic operation might not be a challenge anymore, because as long as you have communication there, they can be adaptive. And the IBR fault response, they are very changing and uncertain due to various factors like operation mode, solar irradiance, and the weather conditions, and the 1547 grid compliant and the different scenarios, different controls. Yeah, definitely very challenging for the protein design. Plus small line impedance and the groundings also affects the protein design for the microgrid. And for the traditional protection design, apart from the overcurrent or directional overcurrent, and we need to add additional protection on top. For example, voltage values like a voltage RMS, positive sequence component, and also the negative sequence component, current component, rate of changeover as well. This approach might work under specific operating conditions. They cannot operate with all different scenarios, or otherwise they be tuned all the time. So this is what we find out. And the data-driven approach has a really good potential there, very fast detection, and they request reliable and large data set for training. And we will improve the classification accuracy. So this is what we find out. And so that's all. Thank you very much for your time. I know this is a big presentation, including too much information there. Hopefully you enjoyed and learned something from our work. Yeah, thanks. Yeah.
Great, thanks, Jing. Well, one thing here is that